We got a drop today on Alpha Centauri and the new Artemis 2 mission that just happened yesterday. They just shot 4 astronauts up into space. We going back to the moon, y'all. Ain't y'all excited about that? I know I am. I've been waiting for this for 41 years. They say something like 50, but I'm not 50 years old, so I could only possibly be waiting for 41. So, but anyways, let's hop into this thing and let's get to the bottom of it. You feel me? Let's go.
Alpha Centauri star system is 4 light-years from Earth, our nearest galactic neighbor. A privately funded venture called Breakthrough Starshot has a plan to send human technology there in the next few decades. To do that, the first interstellar spaceship will have to be extremely light and extremely fast. Pete Worden, the former head of NASA's Ames lab, now leads the Starshot project.
Well, the real question that we've got is there life elsewhere? Are there other Earths?
In Starshot's master plan, which could take flight 2 decades from now, a mothership orbiting Earth will launch a tiny probe called a nanocraft. The nanocraft will carry data-gathering electronics on a one-way mission to the Alpha Centauri system. Once outside the mothership, the nanocraft will inflate a spherical sail. Next, an Earth-based laser array will fire a tremendously powerful light beam at the spacecraft. In minutes, the laser will accelerate the nanocraft to a fifth the speed of light, so it can make the 26 million mile trip in 20 years. It'll be a dangerous journey, so the project eventually will launch hundreds of inexpensive ships, because many will likely fail on the way. Once the nanocraft arrives at one of Alpha Centauri's 3 suns, it won't slow down, but it'll gather as much data as possible as it whizzes past the stars and planets. With a laser beam of its own, the nanocraft will fire that data back to Earth. Its job is done. But other nanocraft could follow in its footsteps to other nearby stars like Barnard's Star, Tau Ceti, and TRAPPIST-1. It's not going to be easy, but it looks possible.
We assembled, when we started this, about 30 of the world's experts in this, and their first reaction was skeptical. They said, they enumerated probably 25 big challenges. But we started looking at them. Each one of them is solvable in the next couple decades. This is the century that will leave our solar system and become a galactic species.
All right, let's get it, y'all. I'm ready to go.
The closest star system to Earth is hiding mysteries. Just 4.37 light-years away, the Alpha Centauri system contains 3 stars: Alpha Centauri A, Alpha Centauri B, and the faint red dwarf Proxima Centauri. In 2016, scientists found Proxima b is our closest potentially habitable planet, but the real mystery is Alpha Centauri, where planets may exist yet remain undiscovered. Scientists still haven't confirmed planets around Alpha Centauri A or B. If they exist, they could be some of the closest worlds humanity might ever explore. The universe may be full of nearby neighbors we haven't seen yet. Map the cosmos with curiosity.
So what's up, y'all? Y'all really think we gonna do it? Y'all think we gonna go? You think we can get there? They talking about this shooting taking this mission, Star Shot, I think it's called. They're gonna start using this thing called Star Shot where we're going at the 20% of the speed's light or light speed or whatever you want to say. 20%, bro. That's pretty fast, right? So they talking about we can reach Alpha Centauri in like I think they said like 20 years or something, bro. Man, I hope we do it, bro, because I'm so curious. And it's crazy because it might not even happen in this lifetime of mine. But that's so good to know that I'm a firm believer in reincarnation and I'll at least get to see it sometime down the road. No, let's get back into it though.
34 million miles per hour. Our nearest star, Alpha Centauri, is 25 trillion miles away. With today's fastest spacecraft, it would take 30,000 years to get there. But what if we could do it in just 20 years? Meet Project Starshot, a spacecraft smaller than your phone, but powered by the most powerful laser array on Earth. No rockets, no fuel. Just a light sail thinner than human hair accelerated by 100 billion watts of laser power to 20% light speed in just 10 minutes. This tiny probe weighs only 1 gram, lighter than a paperclip, but it will experience 10,000 Gs of acceleration. That's like going from 0 to 134 million miles per hour faster than you can blink. Stephen Hawking called this humanity's next great leap. Are you ready for interstellar travel?
Yes,
The
sir.
star Proxima Centauri is about 4.25 light years from Earth. How long would it take you to travel there on a spaceship that can instantaneously accelerate to 99.9% the speed of light and immediately stop when it gets there? If you think it's a little more than 4 years,
Yeah.
you are completely wrong.
Why?
You would arrive in 65 days. This is called time dilation, and it happens to anything traveling close to the speed of light. As you get nearer to the speed of light, your time goes slower. There's no theoretical limit to how far you could travel in your lifetime, even to distant galaxies. But the rest of the universe keeps aging at the normal rate, so you might not find what you expect when you get there.
Hey, I ain't gonna lie, I'm a little confused because I swear they said that Alpha Centauri is 4 light years away. Now, I've always thought that that means if you're traveling at the speed of light, it's gonna take you 4 years to get to wherever you're going, right? That's the light speed. Now, this person just says 65 days because it's time dilation. Well, just when you feel like you know what's going on, they throw another wrench in there and confuse the hell out of us. Why do they do this?
Dream. The idea of reaching another star, like Alpha Centauri, has captured our imagination for decades. But how do we overcome the monumental challenges of traveling such vast distances? This is where an exciting new concept comes into play. The Sunbeam mission, which proposes using relativistic electron beam propulsion to send a spacecraft beyond interstellar space. In this video, we're diving into what makes this idea revolutionary, the science behind it, and why it's such a significant leap for humanity. At the heart of the Sunbeam mission is a unique propulsion system that relies on relativistic electron beams. These are streams of electrons accelerated to nearly the speed of light. The beam would push against a spacecraft, allowing it to achieve incredible speeds, up to 10% of the speed of light. This means the probe could reach Alpha Centauri, our closest star system, in just over 40 years. Why electron beams? Unlike conventional propulsion, which carries fuel on board, Sunbeam uses an external power source. This removes the need for heavy fuel, reducing the spacecraft's mass and making higher acceleration possible. Moreover, electrons are relatively easy to accelerate compared to other particles, making this method more efficient. The physics behind this is fascinating. At such high speeds, a phenomenon known as the relativistic pinch effect comes into play. Typically, electrons repel each other because they carry the same negative charge. However, at near light speeds, time dilation prevents the electrons from pushing apart, keeping the beam coherent and focused over vast distances. This allows the beam to provide consistent thrust even far from the sun. This method differs significantly from projects like Breakthrough Starshot, which relies on laser beams to propel tiny, lightweight probes with light sails. While Starshot's approach is innovative, its small probes, just a few grams, lack the capacity for meaningful scientific instruments. Sunbeam, on the other hand, aims to propel a spacecraft up to 1,000 kilograms, the size of NASA's Voyager probes. This opens the door to robust scientific missions, allowing for detailed exploration and data collection. Key to Sunbeam's success is the Statite, a stationary satellite positioned near the Sun. Unlike orbiting satellites, the Statite uses the Sun's radiation pressure and magnetic fields to remain fixed in place. From this vantage point, it can direct the electron beam toward the spacecraft. A massive sun shield protects the Statite's sensitive components, ensuring it operates in the Sun's intense heat. This innovative platform is crucial for maintaining the beam's alignment with the spacecraft over extended periods. While the Sunbeam concept is scientifically exciting, turning it into reality presents significant challenges. One of the first hurdles is generating and maintaining a high-energy electron beam over vast distances. For context, the beam may require energy levels reaching 19 giga-electron volts at 100 astronomical units from the Sun. Although this is within the range of current particle accelerator technology, such as the Large Hadron Collider, creating a coherent beam over interstellar distances is uncharted territory. The beam's energy source, the Statite, needs to harness the Sun's immense power efficiently. This involves converting solar energy into electricity to drive the beam. High-temperature thermionic converters, capable of operating near the Sun, could play a vital role in this process. These systems are under active research, and their development is critical to the mission's feasibility. Another challenge lies in the spacecraft itself. Unlike traditional missions, which rely on onboard thrusters, the Sunbeam spacecraft must be designed to handle continuous external thrust from the electron beam. This requires advanced navigation systems to maintain stability and ensure precise trajectory adjustments during acceleration. Material durability is equally important. The statite must withstand extreme conditions near the sun, including intense radiation and temperatures exceeding 2,500 degrees Fahrenheit. Missions like NASA's Parker Solar Probe have demonstrated the potential of advanced heat-resistant materials, providing a roadmap for developing statite components capable of surviving in such environments. Finally, there's the issue of beam spread. Over interstellar distances, even a slight divergence in the beam could result in a loss of propulsion. Addressing this requires meticulous engineering of the beam generation system, ensuring the electrons remain tightly focused throughout their journey. Despite these challenges, the concept remains within reach of current or near-future technologies. The success of this mission depends on interdisciplinary collaboration, bringing together experts in particle physics.
The journey to the nearest star system takes 80,000 years with current technology, but scientists have just figured out how to do it in 20 years. This was Stephen Hawking's final project before he died, to send a probe that's smaller than your palm to Alpha Centauri. It's called Breakthrough Starshot, and here's exactly how this thing works. They're building thousands of times.
Acceleration and beam coherence, offering a technological basis for the electron beam propulsion system. The Sunbeam mission also shares common ground with other beam-powered propulsion initiatives, such as the DEEPIN program. This project explores the use of directed energy, like laser beams, to propel spacecraft. While DEEPIN focuses on light-based systems, its research into energy transmission and beam alignment has applications for Sunbeam's electron beam approach. These interconnected discoveries show how cutting-edge science can converge to make seemingly impossible ideas feasible. By leveraging recent breakthroughs, the Sunbeam mission demonstrates how humanity can take bold steps toward interstellar exploration. The implications are profound, not just for space travel, but for advancing our understanding of physics, materials science, and energy systems. Thank you for watching. If you found this discussion exciting, don't forget to like, share, and subscribe for more explorations into the cutting edge of science and technology. Let's continue to push the boundaries of what humanity can achieve.
traveled 6 seconds around the Earth, 13 minutes and 36 seconds to the Moon, and only a few hours to Mars. Sounds absurd, doesn't it? Here are 5 facts about the Breakthrough Starshot project. 1. The small spacecraft are called nanocraft, and they are designed to accelerate to 20% of the speed of light, approximately 60 kilometers per second. These tiny space probes weigh only a few grams and are shaped like tiny computer chips. Each probe is equipped with a camera, sensors, and a communication system. 2. These nanocraft are intended to explore our universe in the future, with the first target being the Alpha Centauri system, the closest star system to us. Among other things, there is an Earth-like planet there where life could exist. 3. Currently, it would take us tens of thousands of years to reach this star system, but with the nanocraft, we could achieve this in just 20 years. 4. The nanocraft will be propelled by a massive laser accelerator on Earth. This laser will direct an extremely intense beam of light at the spacecraft. The spacecraft are equipped with ultra-thin light sails that reflect the laser's light and harness the so-called light pressure. This light pressure generates an acceleration that propels the spacecraft to high speeds. 5. Fun fact. Due to time dilation, the nanocraft would take 20 years from Earth's perspective to reach the Alpha Centauri system. However, from their own perspective, the nanocraft only require 12 years, 1 month, and 2 days for this journey.
About our closest star, a red dwarf about 4.25 light years away. One of its planets is habitable, as in it's in the Goldilocks zone, but it's currently locked, meaning it can't spin because of the gravity of its star. Now, why doesn't that happen to Mercury, being as it's so close to the sun?
Ooh, very good. If you have a planet, or anything that's orbiting close to something else that has strong gravity, tidal forces will slow down its rotation so that it'll only show one face to you. One face to you. And so when that happens, it's called being tidally locked. We have locked the moon. Pluto and its moon Charon are close to one another. They have double tidally locked. They show the same face to one another. Mercury does not, and it's because Mercury has a resonance, okay? Mercury feels the gravity of other objects in the solar system, in particular Venus. And when you feel another source of gravity in addition to that of the sun does not succeed in totally tidally locking the planet.
That makes sense.
Friendly reminder,
Makes sense, right?
Alpha Centauri, the most powerful blue diamond sun that has ever existed in the history of the universe, is only 4 light years from here. Alpha Centauri, we are actually in the gravitational pull of this massive diamond sun. Nothing happens in our solar system without this star system being involved and knowing about it. They're actually in the key B, a different dimension. Here are the 5 different keys that the universe is segmented into. Right here, E, A, D, G, B. The blue diamond sun is the most powerful sun position to have. So since we're only 4.3 light years, that's a musical 4 count, which is accessible via the theta brainwave state, which is 4.3 hertz. So you could travel there in light via the theta state with your brainwaves to the diamond sun. I realize that sounds a little out there, but your brainwaves physically turn into the key of A when they go to 4.3 hertz or 4.44 hertz. That's all the key of A on the guitar. They're just smaller. The guitar is just larger waves. You see, brainwaves are just tinier. So to access a star system, especially a diamond blue one that we're in the gravitational pull of, then you just, relax your body to get to 4.3 hertz and then focus on a diamond sun that we're already in the pull of, and then you're there. And so when we transition to this new state of universal being or whatever, then that star system, Alpha Centauri, is going to be here on Earth dominating. A diamond sun is the most powerful. They're It's incredible.
I think the planets around Alpha Centauri and Proxima Centauri, which are the closest star, it seems like there are planets around those now. And I think that was interesting because we could conceive of going there.
Right.
I mean, there was this idea, Stephen Hawking actually and some others, before he died, had this idea called Breakthrough Starshot, which is the idea to send a little probe out to the Alpha Centauri system. And I think in their view, Yuri Milner as well, the entrepreneur, wanted to do that. And I think it's something like 100 years travel time or something with our current technology. And they pointed out that we don't do that now. We don't think 100 years in the future. And if you go back when people were building cathedrals, people used to routinely start projects that would take 100 years to bear fruit. Yeah. And so we could imagine going there. And that then becomes fascinating, I think, because then you've got a solar system, another solar system that you could go and visit conceivably.
And I mentioned that to the next door neighbour star, out of the 300 billion in our galaxy, using current technology will take 76,000 years. Yes, which is a bit of a downer. Yeah. But with Breakthrough Starshot, they're using something called a solar sail, and you can actually shine laser light. So laser light is light, photons, and you can accelerate it in space to about a fifth of the speed of light.
Wow.
Warp factor a quarter. But for any Trekkies. But yeah, you can accelerate it, and it will just take 20 years to get there. And so, the thing is, the thing you send out there, it has to be incredibly light, so it weighs about 1 gram.
Okay.
So 1 gram is about
what on Earth would weigh 1 gram?
Well, a very small chip.
A chip.
Yeah. Yes, and that will be
like
at the
a Dorito,
heart, and it will sort of send the solar sail to the next door neighbour star system, and then you can actually see. And things we might be able to get the answer is there life out there? But the thing is, because it's sending something so small, I know. And it's funny. I think it's too many thoughts. As humans, we don't want to be alone. We want to find life. There's lots of research
there's life out there.
Solar system,
definitely life.
We will reach Alpha Centauri, the triple star system, which is the closest star system to Earth, located at about 4.37 light-years away in the constellation Centaurus. It is a triple star system consisting of 3 stars, Alpha Centauri A, Alpha Centauri B, and Proxima Centauri. Alpha Centauri AB is a binary star system made up of Alpha Centauri A and B, which are sun-like stars, classified as Class G and K, respectively. These 2 main stars have an apparent magnitude of -0.27, making them appear to be a single star to the unaided eye. Only Sirius and Canopus are brighter than it, making it the brightest star in the constellation and the 3rd brightest in the night sky. Alpha Centauri B is smaller and colder than Alpha Centauri A, with 0.9 solar mass and less than 0.5 solar luminosity. While Alpha Centauri A has 1.5 times the luminosity and 1.1 times the mass of the Sun. The two have a 79-year orbital period around a shared center. The distance between A and B fluctuates from 35.6 astronomical units, or roughly the distance between Pluto and the Sun, to 11.2 AU, or roughly the distance between Saturn and the Sun, due to the eccentricity of their elliptical orbit. In the Alpha Centauri system, Proxima Centauri is the star nearest to the Sun, located approximately 4.2 light-years from Earth. Robert Innes, a Scottish astronomer, made the discovery of the star in 1915. Proxima Centauri is a red dwarf star, which is the most common kind of star. It is roughly 7 times smaller than the Sun, and a little more than half as hot at 3,100 kelvins. On the other hand, our Sun is 5,772 kelvins. As a matter of fact, this little star is just 50% larger than Jupiter. Red dwarf stars have long lives because they consume hydrogen fuel very efficiently. Proxima Centauri is expected to remain in its current state for more than 4 trillion years.
Damn, I know that.
Although the Alpha Centauri system can be seen in the constellation Centaurus, Proxima Centauri is usually not visible to the human eye. Proxima Centauri orbits the other 2 stars in the system, Alpha Centauri A and B. Proxima Centauri takes 550,000 years to complete an orbit of A and B. With an apparent visual magnitude of 11, Proxima Centauri is the dimmest of the three stars.
I wonder what this is about.
This star emits light at a slower rate than the Sun, with a luminosity of 0.17% that of the Sun. However, Proxima Centauri is categorized as a flare star, which is prone to massive solar flares, because its brightness can vary by more than 1 magnitude in a matter of minutes.
Wow.
To reach the nearest star system, a chemical rocket would take 740,000 years. But there is a type of spacecraft that, without any fuel and relying solely on light pressure, can cross 4 light years in just 20 years. This isn't science fiction, it's the Breakthrough Starshot laser sail project that's currently underway. The principle is frighteningly simple. Light actually has pressure. Photons have no rest mass, yet each one carries momentum. When trillions of photons strike a smooth surface, it's like billions of photon ping-pong balls bouncing continuously, accumulating into a considerable thrust. At the heart of the project is a probe the size of a postage stamp, weighing just 1 gram. It must carry a camera and communication equipment and travel toward Proxima Centauri at 20% the speed of light, 60,000 kilometers per second. What propels it is a 4-meter-wide light sail, thin as a cicada's wing, powered by a ground-based light cannon made up of a 100-gigawatt laser array. But this path is filled with deadly challenges, starting with the threat of interstellar dust. Traveling at 20% the speed of light, even a tiny speck of dust could deal a catastrophic blow to the probe. Calculations show that dust particles larger than 15 micrometers in diameter can pose a threat to the spacecraft. Even worse, a light sail just 1 micrometer thick has over a 90% chance of being pierced by dust during its 4 light-year mission. Scientists have come up with an ingenious solution. During the initial phase, when dust is dense, the light sail is not fully deployed. Instead, it is placed behind a shield and designed with segmented molten aluminum blocks. Even if some areas are pierced, the overall structure can still remain intact. The second challenge is thermal management. When the laser shines on the light sail, it generates enormous heat. The light sail must withstand extremely high temperatures while also maintaining its structural integrity. The solution is to use materials with a reflectivity greater than 99.9999% and to adopt a multi-layer structural design, allowing the light sail to reflect near-infrared light while efficiently emitting mid-infrared light for heat dissipation. The third and most critical challenge is stability control. The light sail must maintain an exact position within the laser beam without the slightest deviation. Even the slightest tilt could cause the light sail to veer off the laser beam and lose thrust. To address this, scientists have designed self-stabilizing light sails based on metasurfaces, using optical forces to achieve passive self-stabilization, allowing the light sail to automatically correct its angle and lateral disturbances. Proxima Centauri, the star closest to us, is itself a world full of mysteries. It is a red dwarf star. Although it is very dim and cannot be seen with the naked eye, it is an active flare star that unpredictably erupts with intense stellar flares. If the Breakthrough Starshot project succeeds, the probe will reach the Proxima Centauri system in about 20 years. After arrival, it will spend about 179 days observing the entire system, and then transmit the data back to Earth in the form of radio waves. Because of the vast distance, these signals will take more than 4 years to reach Earth. In other words, if everything goes smoothly, we could receive the first photo from Proxima b as early as 2050.
The most distant human-made object in existence is Voyager 1. Launched on September 5th, 1977, it has been flying for nearly half a century. At its current speed of roughly 61,000 kilometers per hour, the spacecraft would need approximately 73,000 years to reach Alpha Centauri, the nearest star system to our own, sitting just 4.24 light-years away. Chemical rockets work by burning propellant and expelling the exhaust at high velocity to generate thrust. For reaching another star, it is profoundly, almost insultingly, insufficient. The Tsiolkovsky rocket equation makes the situation brutally clear. The faster you want to go, the more fuel you need, and the more fuel you carry, the heavier you become, requiring even more fuel in a spiral that never resolves. The chemistry simply runs out. The energy stored in molecular bonds, no matter how cleverly engineered, cannot generate the exhaust velocities needed to cross interstellar distances within any timescale that matters to a living civilization. Chemical rockets will carry our legacy outward. They are the proof that we tried, but they will never carry us to another star. They are the first step of a journey whose second step has not yet been invented, and they remind us with quiet mathematical certainty that everything we have built so far is not nearly enough.
So, what would it take for humans or for human-like creatures to travel out to Alpha Centauri?
There's a few different ways of doing it, I suppose. One is, it depends on how fast your ship is. That's always going to be the determining factor. If we devised some interstellar propulsion system that could travel a fraction of the speed of light, then we could do it in our lifetimes, which is, I think, what people normally dream of when they think about interstellar propulsion and travel.
Hell yeah.
That you could literally
get there, bro.
Step onto the spacecraft, maybe a few years later you step off on Alpha Centauri B, you walk around the surface and come back and visit your family. There would be, of course, a lot of relativistic time dilation as a result of that trip. You would have aged a lot less than people back on Earth by traveling close to the speed of light for some fraction of time. The challenge of this, of course, is that we have no such propulsion system that can achieve this.
Let's go, y'all. I'm trying to go.
And here they are, NASA's Artemis II crew.
Let's go.
Commander Reed Weissman, pilot Victor Glover, and mission specialist Christina Cook and Jeremy
Going back to the
Hansen
moon,
taking
y'all.
their first steps outside for their historic test flight. Reed, Victor, Christina, and Jeremy now on their way to launch pad 39B, where they will fly to the moon.
All right, man. Let's go. I've been waiting for this so long, y'all. Excited.
10, 9,
8,
8,
7,
7,
6,
RS-25
5,
engines,
4,
4,
3,
3,
2, 1. Lift off,
Booster
baby.
ignition.
Let's go.
and liftoff. The crew of Artemis II now bound for
Oh,
the moon.
man, let's go,
Humanity's
bro.
next great voyage begins.
Yes. I've been waiting, bro. I feel like this was never going to happen.
Good roll pitch. Roger, roll pitch.
Houston now controlling the flight of Integrity on the Artemis II mission around the moon.
Integrity, AMT high. AMT high.
On time, passing 30 seconds onto the flights.
And it was successful, y'all. They did it. They up there.
Mission Control Houston.
It's going to take them like 10 days or some shit like that. They ain't going to be there. I think they might just be flying around it this time. I'm not sure if they landed on the moon. I don't think they landed on the moon this time. But I think they're going to drive around that bitch. Ain't it so weird how it just curves and then it looks like it's going straight. Then it kind of looks like it's coming back down to earth. It blows me away. That's why I say you got to do all your own research, bro. Don't just be believing shit because you see it on here. Because AI, graphics, liars, this, that, and the third.
Have you the same?
Look, it looks like it's coming back down.
Communication signal transfer.
But they said it was successful. They said they up there. So.
Approaching 90 seconds into the Artemis II mission. Integrity is 14 miles in altitude, 8 miles downrange, traveling more than 2,600 miles per hour. Minute 50 seconds of mission elapsed time, standing by for main engine throttle down to 85%, ahead of solid rocket booster separation.
Man, I wish I could be on that rocket, man. I'd have gave anything to be able to go, bro.
We see throttle down?
I'd have gave anything to go to the moon, bro. To be on that rocket, just to go out there and experience that.
Confirmed
I know
separation.
the people up there are so going through it, so
main
excited,
engine throttling
bro.
up, guidance converged.
All right, y'all. That's the clips for today, man. Yeah, I guess we got a mission going to Alpha Centauri pretty soon, man. They talking about we gonna probably be there by like 2040 or 2050 or something. We're gonna actually be able to see the sunset or something. They was talking crazy, bro. Like I'm excited for it. And this thing right here, this moon stuff right here, bro. I'm super excited for that because this is gonna be done in a couple weeks probably. So we're gonna we doing it. We're gonna be space bearing ass people again, bro. And I'm loving it. I love this kind of stuff, bro. But I'm gonna keep on bringing some more clips of this stuff to you guys. I just need you guys to like, subscribe, and follow me, man. I'm waiting to get this little check. I'm about to get some studio equipment so I can make these videos a lot better. I know the quality ain't been the best, but I'm just starting. I'm getting off on to my thing with you guys, man, and I just want some loyal people to ride this thing out with me, man. So you ride with me. I'll make sure to keep on delivering the content. I'll bring some good stuff. You guys tell me what you want to see, and I'll make it happen, man. But we're gonna event up. We're gonna get to the bottom of this. You feel me? And like I say, live for today, cause tomorrow ain't promised. And I'll see y'all tomorrow.